Welcome back to our review videos. We're going to look at the next requested topic, which was classifying compounds as either ionic or covalent or metallic, and how to name them. So first of all, we need to look at a periodic table to get familiar with this again. So here's our complete periodic table of the elements. I'm going to go ahead and sketch in our zigzag or our stair-step line, or maybe I'm not with this marker apparently, but this is where it is for reference. Let's see if I can't get a better one on here. Oh, that's much better. Alright, so there's our zigzag or our staircase line. That's dividing the periodic table between metals and nonmetals. Now remember, to the left of the staircase reside the metals, except for hydrogen, which is a nonmetal, and the rest of the nonmetals are on the right side of the staircase. The noble gases are nonmetals, but they don't tend to react. I mean, we can force them in the lab, but for the most part we say they're totally inert, which is why they're called noble gases. And so when we're talking about chemical bonding, we can essentially ignore this last column or family of elements. Alright? Now, the other category, besides metal and nonmetal, on the periodic table is the metalloids, which are not color-coded on this particular periodic table. So let's just go through and point out the individual metalloids here. They are elements which touch the staircase line, except for aluminum, which is just a metal. Okay? It hangs out with the metalloids, but it is just a regular old metal. Boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and depending on who you're talking to, astatine may or may not be. Consider it to not be for our purposes. But general rule of thumb, touching the staircase makes you a metalloid. And that means you have properties in between a metal and a non-metal. You can conduct electricity, sort of, so you're a semiconductor. You're a solid, but you tend to be brittle. Okay? They have melting points and boiling points that are in between the covalent compounds and the ionic or the metallic compounds. So they're just kind of in the middle of everything, which is why they're touching this staircase line. Alright, when we're looking at compounds, to determine if you are ionic or covalent, first of all, you need to determine the identity of the first element. So, if I write a series of compounds, let's say potassium chloride, iron 2 oxide, aluminum, let's do aluminum sulfide, carbon dioxide, dinitrogen dioxide, and sulfur trioxide. We look at the identities of the first elements. So potassium, iron, aluminum, carbon, nitrogen, sulfur. And we find them on the periodic table. Potassium is a metal, which means this compound is going to be ionic. We look up iron. Well, you know what it's going to be, but let's just make sure on the periodic table. It's right here. It's a transition metal, so a metal, which means ionic. Aluminum touches the staircase, but still a metal, so ionic. All three of these are ionic compounds. Down here, we look up carbon. It is to the right of the staircase, and it's not one of the elements that's touching it along the edges. So, carbon is a non-metal. And if we have a non-metal in the first spot, we're dealing with a covalent compound. Okay? Nitrogen and then sulfur, non-metal, non-metal. So these three are covalent compounds. Metallic compounds are generally considered just alloys, and when we're talking about that, you look at the first element again. So let's say we have silver and gold mixed together. Because technically these are a solution. They're not an actual chemical bond, but when they solidify, they do form attractions to each other. So this is a metal. The second element is also a metal. It's not a non-metal like it is up here. And so we know that this bond is metallic. Okay? Let's look at naming some of these compounds. If I have a metal from group 1, group 2, group 3, or silver, cadmium, and zinc, they're all going to follow the same rule, and those rules are the type 1 rules. To summarize the type 1 rules, we're going to write the name of the first element without changing it. Then we're going to have a second word, so I'm going to indicate that with a plus sign. We're going to take the root of the second element and then add the suffix IDE. Okay? For example, if we're looking at the compound MgO, Mg is magnesium in group 2. So I write the name magnesium. O represents the element oxygen. Now the root of oxygen is ox. I chop off the YGEN part and I replace it with the suffix IDE to show that it is in a compound. And we read this together, magnesium oxide. If you're looking at one of the exceptions in the periodic table, let's say AgCl, we write it same way as here. So Ag, we look up and we see that it is silver. So we write silver. Then we put a space and we look for Cl. Well, Cl is chlorine in the halogen family. So I'm going to write chlor, C-H-L-O-R. The ene gets dropped and replaced with the suffix IDE to show that it is a compound. Silver chloride. Okay? And let's just do one that has fluorine, because fluorine takes on some tough spelling when it's in a compound, or just in general, because everyone always forgets how to spell fluorine. L-I-F. Li is lithium. F is fluorine, of course. F-L-U-O-R is the root, fluor. It's actually Latin for river. And then you replace the ene with ide, lithium fluoride. Or if it helps you spell it, you can sort of pronounce it in your head as fluoride, if you hear the distinction there. Fluor. Just a little help on the spelling there. Alright? So those are all type 1 compounds. Type 2 are still binary compounds, binary ionic compounds, so a metal and a nonmetal, but now we're picking from the transition metals, except for silver, cadmium, and zinc, which are in the last category, and also including tin and lead over here in group 14. They act like the transition metals, these act like the representative or main group metals. So, if I'm looking at a type 2 compound, the naming process is very similar. Okay? I name the first element. But here's where it's different. I attach to that name a Roman numeral of the oxidation for that metal in parentheses. This is all part of the same thing. Then I'm using a plus to signify a space, and then we do what we did for the first type 1 compounds, is the root of the second element, suffix IDE. So let's pick on iron for this example. Iron can have 2 common oxidation states. So we'll go FeO and Fe2O3. Going by the original rules for type 1 compounds, both of these would be named iron oxide. But that's no good because they have different chemical formulas. They are both oxides of iron, but how do we know which one? Well, that's where the Roman numeral comes into play. We do know the charge, or oxidation, on oxygen. It's in group 16, which means it's a -2. So I'm going to write -2 above the oxygen in both compounds. Compounds overall have no charge, and that's the key when we're figuring out the Roman numeral. None of the oxidation numbers, when I total everything up, can add to anything other than 0. So -2, there's an implied subscript of 1. I'm going to go ahead and write it so you can see where it's coming from. So we multiply these two together, and there's a -2 in this half of the compound. Well, iron has to cancel out that -2 charge, so it gets a +2. There's only one atom of iron to accept that +2 charge, therefore every iron atom in FeO has a +2 oxidation state. And so we're going to write it as iron, parentheses, Roman numeral 2, close parentheses, space, and oxide, the root of oxygen and the suffix IDE. And we read this as iron 2 oxide. The second compound is still an oxide of iron, so it's still a -2 for the oxygen, but now there are 3 oxygens, totaling a -6 charge. You can think of it as -2, -2, -2, add them all together, and you get a -6. Alright? Well, iron still has to cancel out all of those negative charges, which means the irons have to have a total charge of +6. That way these two add to 0. But irons, there are 2 in the formula. Okay? They can share this oxidation. So instead of it being iron with a +6, we divide this +6 by 2. And each individual atom of iron only has to have an oxidation of +3, making this iron 3 oxide. And that's all there is to determining the Roman numeral in a compound. Okay? The type 3 compounds, still binary, but this time they are covalent compounds, where we have a non-metal plus a non-metal together. So we have something from this tiny, tiny wedge on the periodic table. It's not a whole lot of elements. It's just carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, selenium, bromine, iodine, and astatine. That didn't even take that long to read. So if your element in the first position is one of those few elements, then you have a type 3 covalent compound happening. And to name one of these, we use the prefix system. So we're going to write the prefix for the first element, attach it to the name of the first element, plus the prefix for the second element, attached to the root of the second element, attached with the suffix IDE to signify that it's a compound, where the second element comes from the periodic table. And our prefixes are mono, di, tri, tetra, penta, hexa, hepta with a P, octa, nona, and deca. And they're just the numbers 1 through 10 in order. Unlike the ionic compounds, where we're doing a little bit of crisscrossing and math to figure out least common multiples, greatest common factors, doing all sorts of things there, these prefixes literally tell us subscripts. So, for example, carbon and oxygen can combine in multiple proportions, CO or CO2. Well, when we're naming this compound, we're going to name our element, so carbon. It doesn't have a prefix, so it's implied to be a 1, so we could write monocarbon, but there's a special little rule that says if it's mono on the first element, don't write it. So we just write carbon. Then put a space, and we're going to have oxygen. Again, no subscript. Therefore, prefix is mono because the subscript is 1. We do not drop it in the second position, but what we do drop is the O at the end of mono because oxygen also begins with an O, and it's just a pronunciation thing for English. Monoxide is very awkward to say, and so we get rid of that second O and just read it as monoxide. Purely convenient. So carbon monoxide. This one, carbon 2 on the oxygen, so dioxide. Nitrogen has even more combinations. You could have NO, N2O, NO2, NO3, N2O2. The list goes on. I'm not going to write these names, but we have nitrogen monoxide, dinitrogen monoxide, nitrogen dioxide, nitrogen trioxide, and down here, dinitrogen dioxide. I will write that one out. Notice we're also not simplifying subscripts for the type 3 compounds, because you're not allowed to. This isn't about simplifying charges, this is literally the molecule. Its structure has 2 and 2 atoms, so we show those 2 and 2 atoms, which is why we use the prefix system of names in the first place. The last kind of compounds aren't binary at all, they are ternary compounds. And these are always ionic. Now the thing about a ternary compound is they're using things called polyatomic ions. And inside of a polyatomic ion, for example, sulfate, sulfur and the 4 oxygens are actually covalently bonded to each other. And this is in fact what sulfate looks like as an ion. I could throw in all the extra electrons too, to make the dot structure proper. And it has a charge of -2. So inside of that ion, there are covalent bonds happening. But it is an ion, meaning it has a charge. And so when it combines with something, it does it just like the type 1 or type 2 does, by attracting the opposite charge. So I could have compounds like, let's do magnesium sulfate, MgSO4. Now notice, I read the name already. We write the name of the first thing, the first ion, and then we write the name of the second thing. Now we look up SO4 in our reference tables and we see that its name is sulfate. ATE ending instead of IDE. That's how we know, if we don't have this, that we're dealing with a polyatomic ion, that we have a ternary compound, and that there's oxygen in this thing. That's what that ATE is telling us. So we don't change it. We just write it as is. So the rules for ternary compounds: name the first ion, name plus, not minus, name the second ion. That's it. If it's polyatomic, you don't change it. So NH4PO4, or rather NH43PO4, to keep it charge balanced, is ammonium. That's the NH4 part. And then phosphate. Now, notice I've got these parentheses. That's telling me I need 3 ammoniums to cancel out the charge and 1 phosphate. So NH4 with a +1, NH4 with a +1, NH4 +1, and then sulfate with, not sulfate, I just changed my ion randomly, phosphate, let's try that again, phosphate with a -3 charge. +1, +1, +1, -3, the charges cancel out. So NH43PO4, ammonium phosphate. You could have anything in that first position that makes an ion, so it could be a metal. If I combined phosphate with calcium, I would have calcium phosphate. With silver, I would have silver phosphate. Aluminum, I would have aluminum phosphate. If I combined it with another polyatomic ion, it would have to be positive, so that would limit it to ammonium. So ammonium phosphate, which was the example I used here. Or I could use a transition metal from inside here. I would say iron 2 phosphate or iron 3 phosphate to say which oxidation the iron is in. And that also applies to tin and lead. So if I do tin and lead as an example here, because I haven't used them yet, let's do tin. And let's say tin combines with, let's do, sulfate. Arguing with myself. Alright, tin, symbol SN, sulfate, symbol SO4. Tin can be a +2 or a +4. Sulfate is always a -2. So let's say this is tin 2 sulfate. Then I would have SnSO4. But what if I had the formula Sn parentheses SO4 parentheses 2? Well, now I know that sulfate, because it's a -2, I multiply. There's a -4 charge over here. There's only one tin to take it up, so that's a +4 on that tin. So this becomes tin 4 sulfate. 2 words. There's a space there. And just to make sure, it's the last part of this video, that you have your exceptions down, the transition metals that don't need Roman numerals are silver, cadmium, and zinc. And you will find them in this backwards L on the periodic table. Silver is a +1, cadmium and zinc are both +2. So if it helps you remember, the 2 stacked on top of each other have a +2. The 1 by itself, +1. The exceptions for the regular metals, the representative metals that act like transition metals, are tin and lead. Which can have +2 or +4 oxidation states. So, no Roman numeral, Roman numeral. And that concludes this tutorial video.